Thank you very much, Costa. Thank you very much also for inviting me to give a talk. Very much, Levin, for inviting me to visit the University of Waterloo. Okay, so and this is because of the microphone, right? So it's not part of the. It's not how I usually am, but okay. So the talk today is going to be about dimensions of Bateman's convex set, and I mentioned to several people already that in the beginning of the talk, if you work with convex sets, you may find things a little bit too trivial, maybe. But, you know, just stay with me because things will get a little bit more complicated towards the end. So the first iteration of the talk, I'm going to talk about an older result from 2016 with my co-authors David Yost and Tian Sam. And then we'll talk about the newer results of the event. So let me start with just recalling the definitions and setting up things, right? So what are we going to work on? So suppose that we have some closed convex set C. Everything is going to be finite dimensional. And then I would like to look at the faces of this closed convex set and look at the dimensions of faces. So I'm going to go through some definitions. Right, so some subset of C, closed convex subset of C, like this, is a face. If the following algebraic condition holds, so for any x in F and any y, z in C, such that x is in the line segment, in the interior of the line segment connecting y and z, we have y and z in F. So we need this algebraic definition because for convex set, general convex set, like if you work with polytopes, you know that faces can be defined using supporting half spaces or supporting hyperplanes. You can't quite do it for convex sets. You would need to have supporting half spaces for faces and for faces of faces and so on. So it need a definition. But the idea, right, is that if I take something like a triangle and I have a point X here, then to see that, say, this edge of the triangle is a face, right, then I will, if I pick any y and z such that the I in C and X is in the relative interior of that segment, then automatically both y and z should be in the face, right? So it's just a formalization of a very natural thing, right? So if we look at some very basic examples, right? So if we look at something like a tetrahedron, for example, then if I list all faces of a tetrahedron, then I will have the tetrahedron itself. Then the facets of the tetrahedron, right? There's two-dimensional things, edges, vertices, and the empty set. I wouldn't be interested in the empty set. Okay, so then, for example, if I have Euclidean wall, then the faces are going to be, well, let's say much simpler, or there will be two different types of faces. Then the faces will be the ball itself. And every point on the boundary will be also a face, right? And let's look at one more set. And this is more, but if you don't work with geometry of convex sets, maybe that will be still interesting. And maybe for people who work on geometry of convex sets, it's maybe a little bit boring. I just take something like this, kind of like a cone, right? So then again, if I list the faces, I will have the whole set. Let's call it a cone. Then I will have the disk, the base. Then I will have line segments on the boundary. And then the one-dimensional, zero-dimensional faces that are like extreme points. So that will be the boundary of the disk and this kind of apex. So apex and points on the boundary of the disk. Okay, so we can list the faces, and I'm not going to list the empty faces. Every convex set has the empty face, but I'm going to forget about them. So now every face has a dimension, right? So every convex set has a very well-defined integer dimension. It's a dimension of the smallest affine space that contains this convex set. But you can think about the maximal linear independent system of vectors within t minus x, where x is some point in c. So it's a very obvious thing, right? So if I look at this set, for example, and I want to actually write down the dimensions of different faces, that then the tetrahedron itself will have dimension 3, the facets will have dimension 2, the edges will have dimension 1, and vertices will be 0-dimensional, right, faces. So continue with the ball. So for the ball itself will have dimension 3, points on the boundary dimension 0. There's no face with any other dimensions. And for this cone, so the cone itself has dimension 3, base has dimension 2, boundary segments have dimension 1, and points and boundary have dimension 0. Right, so you can do it for any convex set, of course. But now we can reverse the question. So that's the main question. So if we have a closed convex set, we can write down the dimensions of the faces, right? Straightforward thing. But if I write down dimensions, can I then get a convex set that has faces of exactly those dimensions? And we can give it a name. So we call dimensions of faces the facial dimension signature. So I'm probably hitting, I can probably still write it here. Right? So facial dimension signature of C is all dimensions of faces of C. Dimensions of faces. And I can write face like this. Right? That means that F is a face of. Okay, so let me write the question. The question 1, given some set of integers, the negative integers, a finite set of non-negative integers, is there a convex set, closed convex set with this signature? Write it like this with signature. So it's like the kind of question you look at it, you go like, yes, of course, and it is true, right? So it's not a super difficult problem. So I wrote a paper with David Jensen about this in 2016. So we found a construction, completed construction, which gives this kind of set, right? So just to prove, yes, indeed, that is true. And here's how you can construct a closed convex set for any kind of signature. Okay? So let me show how this works. So what we use is Minkowski addition. Again, this is very basic. So remember Minkowski addition of two sets of eigennature, but in particular of two closed convex sets, is the sum of all elements in these sets. So if I take something like a line segment, and then I add a disk to the line segment, then it doesn't matter where they are on the plane, right? The shape of the set will be the same. And what I do, I take one of them and I kind of add it to every point of the other set, right? So to see what happens, we just kind of add a line segment to every point here. So of course, we'll have something like this, and the resulting sum will be a set that looks like this. Right, so that's the sum. And the very valuable thing about this is that if I pick any face of the sum, I can always represent it as a sum of faces of the original set. So I can somehow track the dimensions. I can lose things, of course, right? Because say for this face, I add this face with this face. But also I can add faces here that don't generate anything there, but it's not important. So for the construction that we use. So how do I now construct those sets that correspond to sequences or signatures? So let's do it using the construction that we sort of came up with. So suppose I want to cover something like this. So I start with the first two numbers. So I will order those integers, right? So that. And also for now, I'm going to always use sets of integers that have 0 in them. So say I have something like this, then I will start with a disk to satisfy the first two numbers. Then I will add to this disk a Euclidean ball of dimension 3. So maybe it's better to, because I'm going to do it in 3 dimensions, so to easier draw the pictures, I'm going to put this disk in a plane. So it leaves in a 3-dimensional space. And then I'll add Euclidean ball. So I will get something like something that has a disk on top and disk at the bottom, and then kind of the sides, they generated from the sphere, right? So it's actually, in this particular case, it's actually the convex hull of a torus, right? So some people here are working on toruses, so right? So that's a kind of object. Okay, so now, right? So we have the face of dimension 2, we have faces of dimension 0, and this entire thing has dimension 3. And I can do it for any sequence. So, for example, and there's not so many examples that we can draw because we quickly run out of dimensions, right? So combinatorially, there's not a lot of sequences that for which no number is greater than 3, right? So I cannot draw too many pictures. So for example, if I get 0, 1, 2, 3, then I'll take a line segment, add a disk, and then add a Euclidean ball. So the resulting set will be something like this on top, something like this on bottom, and then this kind of boundary, right? So I'll get a set that looks like this. So they actually look very cute, and somehow there is some interesting things that happen with spatial structure, right? So, and with the shapes. Okay, so something like this, right? So I'll have these faces of dimension 1, faces of dimension 0 in many places, space of dimension 2, and so on. So this construction works for any dimension, right? So this is definitely a yes. And the only thing, right? So there's no need to write a general result because that's what we do, right? So we pick the first two numbers, make a construction for the first two numbers, then extend it to the next number, and so on, right? So if my ordered somehow signature is going like this, right, then I will take the D1 ball, then add the D2 ball, and so on until DM. So the only thing that remains here is to think about sets that do not include 0. And there's a very simple trick. So for instance, if my dimension signature is like this, it shouldn't have 0. So 1, 3, for instance. Then what I'm going to do first, I'm going to subtract smallest number from every member of the sequence. I'll make the construction for this one. So in this case, the disk. And then just add take the direct sum of this set with the space of this dimension, in this case R1. So I'll get a set like this. Right, so it's like, right, so it's like you take the disk and extend it. It's like an infinite cylinder, right? So this will have faces of dimension 1, of course, right? That would correspond to faces of dimension 0 here. And the whole thing will have dimension 3, right? And this was dimension 2 originally. So that also works for anything, right? So if 0 is not in the subset, you just shift it and shift it back somehow by adding the space. Okay. So the first time I gave a talk about this, yeah, there were many questions. So the first question, not many questions, but kind of important questions. The first question was about facial exposure. So the problem with this construction is that the sets I generate are not facially exposed. So, for example, in this set, if I pick this point, it's a face of the set, but I can't find supporting line to the set, supporting hyperplane in this case is a line, or supporting half space, such that it exposes jet at one point, right? So whatever I try to do will expose maybe this face or some faces here, but I can never do it for this face. That's an important property for optimization and basically for convex geometry. So this construction doesn't work for that. And another question was if there is a construction that gives a spectrahedral. Right? So these things are not spectrahedra. So question 2, instead of just this, we want facially exposed. And also spectrahedra, but you will see that spectrahedra will somehow emerge automatically. So now we're going to start talking about the work of design. It's very recent. And this was with Tian Shan and David Yost. Okay, so the answer to this question is also yes, but we need to use a different construction, which is also very simple. But by the way, are there any questions, comments, corrections? Okay. Sorry? I don't hear you. Yes. Oh, and spectrahedra, they are feasible regions of semi-definite programming problems. So for people who work on semi-definite programming, they're very important objects, right? Practically and theoretically as well. But perhaps in this context of somebody who is just studying convex sets, it's just a cute type of convex set, right? So geometrically, you take the cone of positive semi-definite matrices, intersect it with an affine subspace, and then you get a spectrahedron. So it's kind of algebraically defined object. So, but I'm not going to focus on that. It's probably just a question that is interesting for people who work on semi-definite programming and spectrahedra, that kind of thing. But it's not a very relevant question for this discussion, right? So you can forget about spectrahedra, even though they are amazing and very interesting things. Okay, so let's think about facially exposed sets. Now we're going to use a different construction. I'll start with the same sequence, right? So we want facially exposed now. So at 0, 2, 3. So last time, I was going from the start of the sequence and moving to the end. This time I'm going to start with the end and then work on the middle. Okay, so suppose I want to do this. So I'm going to start with Euclidean ball. That will give me 0 and 3. And then I kind of attach a face of dimension 2, or generate face of dimension 2 somewhere on the surface of the ball. So to me, the easiest way to do it is to slice off a piece of the ball with a hyperplane or with a plane in this case. Right? So I'll just tap the set with a plane, slice off kind of a piece, remove it. Right? So then this set will have faces of dimension 0, 3, and 2, because I somehow attached two-dimensional face that way. Right? And I didn't generate anything else, any faces of any other dimension. Right? So, okay. So it's the intersection of the ball with a half space. I can do it for any other sequences as well. I can just find a set of convenient objects that have a structure that would allow me to slice off faces of dimensions that I want. So for instance, if I continue with 0, 1, 3, I will start with the ball. And then I think that's something that is not that easy to draw. It would be good to have like three-dimensional kind of stuff, right? To maybe 3D goggles to show what happens. But I'll do my best. So I take the Euclidean ball, and I'm going to take a cylindrical surface, right? A surface that really looks like this. Something that I had here. I'm going to take this kind of surface, right? Or this kind of convex set with the interior of the surface. And I'm going to take the intersection of this with this, but I'm going to shift it. So I'm going to make it quite large and shift it a little bit. So the cylindrical surface will only slice off a piece of my set. Right? So maybe, so if I look how this cylindrical surface intersects maybe this kind of equator of my sphere, it will be something like this. Right? And then I have this cylindrical thing. So I will cut off some kind of thing here that will have one-dimensional faces. Hopefully it makes sense. Like I will have a ball, and then this cylinder, the intersection with the cylinder will give me something like this, right? Like similar like to those examples that we use in vector calculus to teach integration over complicated regions and things like this. Right? Okay, so now I can do it for anything else. So I just take my ball, and I can slice off things from different parts of this ball. Right, so whatever numbers I want in the middle of the sequence, I'm just going to take something like the cylindrical surface and just slice off bits of the ball that generate faces of the required dimension. So maybe we can even write those objects down. So I will have something like this. Say, so I can have objects like this. So they generalize what the cylinder is, right? So depending on what dimension you want of faces, you can choose different I. Right? So if I start with, if I'm in three-dimensional space, and I write something like this, right? Clearly it will be a cylinder because the first coordinate is missing. So I get a disk in 2 dimensions, and then the third dimension is 3. And I can move this first coordinate in higher dimensions anywhere I want. So I just take the intersection of objects like this. And then if I'm very careful with C and R, which is not difficult to do, right? So make sure that when I slice off different bits and pieces, they don't actually intersect and don't generate new faces. it is very easy to do, right? So it's not a problem. Making sense? Yeah. Oh, because intersections of facially exposed sets are facially exposed. And actually, yeah, we needed to do some work. Actually, we needed to do a ridiculous amount of work to prove those very simple things. But yeah, but the reason, very good question. The reason is that, right, if original sets are facially exposed and kind of those sets are sort of almost obviously facially exposed, then the construction will be facially exposed. So the answer to question 2 is yes with this construction. Also, once we're done with those integer sets that have 0 in them, we can use exactly the same idea, right, to extend this to any set of integers, non-negative integers that doesn't have 0 in it. So algebraically, that's just adding another coordinate, right, that doesn't participate in equations. So, okay. So now the next question, right? So I would say we have answered that one. And question 3 is where, to me, things become interesting, really interesting. So that was kind of, yeah, it's obvious that we can do it. Let's figure it out. And question 3 is, what is the best representation? So we know here from this construction that we can represent any signature using a particular number of inequalities, right? So given I, there is a closed convex set with this signature, such that it can be expressed through a particular number of convex quadratic inequalities, such that C is represented, let's say, represented by the cardinality of I minus 1 convex quadratic inequalities. Right, so we start with the ball. The ball takes care of 2 numbers from this set, right? And then each one of these sets which we intersect with the ball takes care of each one of those numbers. So of course, you would think, well, maybe there's a way to somehow also intersect these things, for instance, and generate more faces of other dimensions. So maybe this construction is not the best. Maybe we can find a smaller number of inequalities to get this representation. So question 3 is, what is the smallest number of inequalities that such that C has a signature and C is represented using this inequality? Okay, so in some cases, actually, we can do a lot better. And consider this a particular example. So I'm going to just write some algebraic inequalities. Something like this. So, of course, they're convex and quadratic. Hopefully that makes sense, right? So you can think of, right, the actual inequality given a convex region, or you can kind of do it algebraically, write it through positive and definite matrix, things like this. Okay, so now think about this set. There's 3 inequalities. So what about the facial structure? And the set is also 7-dimensional. So what happens? If I think about this algebraically, it's like the variables are all different, right? So I have a 1-dimensional line segment. I'm going to take the direct sum of this line segment for the disk in an additional 2-dimensional space. And then I also add an additional 4-dimensional ball to this, right? So it's a direct sum, a direct product, depending on the terminology, of 3 convex sets, right? So they live in kind of orthogonal spaces. Right? One set is like this, another one is like this. And I get something like that. So in this case, it's explicit. So I take a disk. Sorry, I take the line segment in R1. Then I add this disk in R2. So they will live in R3. And then I add the 4-dimensional ball. It is 4-dimensional, right? In exactly the same way. So then this whole thing will be 7-dimensional. So what happens to the faces? Well, remember how in Minkowski addition, if I look at the faces of the sum, every face of the sum is the sum of faces here, but not necessarily the other way around. So I can find pairs of faces here that don't give me a face there, right? So I can lose something. But it's not the case for direct sum. So the faces of the sum are exactly all possible direct sums of all faces, right? So if I have my convex set C represented like that, then the signature of this, let me just write it like this. So I is the facial dimensional signature. This will be the Minkowski sum of those integer sets. Because, right, because every face here is the direct sum of some faces. Direct sum of some faces of any faces here gives me a face there. And if I think about the dimension of the direct sum of some convex sets, that dimension will simply be the sum of dimensions of individual sets, right? So here, this guy is 1-dimensional, this one is 1-dimensional. Clearly, this one is 2-dimensional. Right? So if I think about what are the dimensions of the convex set, of faces of the convex set, that is defined by this, then it's not that difficult, right? So let's name it something. So let's say this is some C bar. So C bar, because when I'm going to deal with closures, so C bar, the dimension sequence of C bar is the sum of the individual signatures. So of course, we know what those objects are. The first one is the line segment, the signature is 0, 1. The second one is the disk, signature is 0, 2. And the last one is the 4-dimensional Euclidean ball, the signature is 0, 4. Right, so then I just add these things in all possible combinations, right? So I add 0 plus 0 plus 0, I get 0. 1 plus 0 plus 0, I get 1. 2 plus 0 plus 0, I get 2. And so in that fashion, I actually get the entire sequence of numbers from 0 to 7, right? Everything is possible. So it's a 7-dimensional set, and it has every dimension of faces in it, and it's represented by 3 convex quadratic inequalities. So if I use the original construction, that number would be 6. No, 7. Right? Because the sequence starts with 0 and ends with 7. And this construction works for everything like this, 0, 1, 2, and so on, and then 2 to the power k minus 1. Right? Because it's easy to see how you can write, you can keep writing those inequalities, right? And represent this. So if I have this particular sequence, then the complexity of the representation for this specific one is a lot lower than that, right? So in this case, the number of inequalities is log 2 of the cardinality of I. So it gives us hope that maybe even in general, we can find something better than just this, right? So, but we don't know. So based on this discussion, I can write somehow an upper bound and a lower bound, but we have no clue what is in between, right? So we have no clue that the lower bound should be attained always. So an upper bound is, of course, if I is decomposable like this. Right? So if it's actually the Minkowski sum of some other sets of integers, finite sets of non-negative integers, then, well, let me say the number, just the number of inequalities. I don't want to write too much. Convex quadratic inequalities is, maybe that's only precise. Then C can be represented. C with the signature I can be represented by the sum of cardinalities minus, why did I write it like this? So plus IK, right? Minus OK, right? Because so I will use this kind of direct sum decomposition, and then for each one of them, I will use this construction with slicing off bases, right? So that's a very simple upper bound. We also have a lower bound, and the lower bound, it just comes from linear algebra. So you just think about linear subspaces of given dimensions, and if you intersect them in all possible ways, what are the possible dimensions of linear subspaces that you can get? Because that bound will work for phase. So on the lower bound, it's a little bit, I think it's an interesting bound. So this thing cannot be larger, no, sorry, it can be smaller than a particular number. So the number of those convex quadratic inequalities can be smaller than the minimal number such that it's quite lengthy, such that there is some di's that are integer also. And we can kind of cover that I with some kind of an expression. Okay, so I should be the subset of its maximum union with something like this. We get all I that are bounded by so yeah, so that's a bound. So in principle, if we solve this problem, right? So we want to find that we just have an integer sequence, finite integer sequence, and we want to find the smallest k such that there's some numbers or negative integers that our I is the subset of something like this. Combinatorial problem. Then we know it's a lower bound, but we don't know if it's sharp. So it is sharp in one particular case where we have this special sequence, right? So we can use this bound to show that in this case it works, right? So but that's pretty much it. So we don't know. So it would be very interesting to figure this out. And somehow there's some combinatorics coming from a completely continuous problem about dimensions of faces of convex sets. And this also generated a lot of open questions. So I think that's probably the most valuable part of this work, is that now we have a lot of questions to think about, and they are questions that can help kind of discover more things about facial structure of convex sets. So obviously, the first question, they are open questions or conjectures, maybe C1. Right? So the first question is obviously, for any sequence, what is the most efficient representation? Right? So given I, what is the most efficient representation of C such that the signature of C is I? And we can think about most efficient is minimize the number of convex quadratic inequalities that represent that, just the way we consider it. But it doesn't have to be like that. There's other ways to think about it. Number of convex quadratic inequalities. Right. Another way to think about this is for people who are interested in spectrahedra, right? What is the minimal spectrahedral representation of this? Right. So what is the smallest size of SDP matrices that you can use to write down this representation to get a convex set with the signature, right? So spectrahedral smallest. So we can actually write this explicitly as a matrix inequality, quite large. I think it's the matrix is just for one of them is n+1 by n+1 or something like this. Levent wrote it, so he knows better about those representations. And okay, so we don't know. Also, we can think about some specific sequences that are indecomposable, right? Because there's research on integer sequences that cannot be written like this, or that can be written like this, right? So you can think about sequences that are difficult to write like this, or impossible to write like this, or sequences that are easy to write like this, and then, right, think about what is the best presentation for them. So also another kind of dimension of this question for different special sequences, right? So one more question is related to polars and dimensions. So sometimes we want the convex set itself and its polar to both have some good properties. For example, one of the most basic properties that make a convex set good is the facial exposure. So if I take something like this, a cylinder, for example, and then I take the polar set. I'm not going to define polars because maybe that will take too much time, right, to talk about polars and duality. So every convex set has a polar, and like every polytope has a polar. So you know that platonic solids, they are polars of each other somehow and so on. So if I take a polar set of this, then both of these sets are facially exposed. But it doesn't have to be like this. So for example, what could I take, for example? For example, yeah, I can take like a dual of something that is. So I can take a set like this, right? And the polar of the set will be like that. So it's not facially exposed, right? So another question is, if I have a facial dimension sequence, Is there always convex set? I see. With the signature, and such that both C and pole are exposed. Right. So both of these constructions are bad in this sense, because for this first construction, the set itself is not facially exposed. For the second construction, the dual is not going to be facially exposed, or the polar. So I think the answer to this question is yes, but the general construction is unknown. And then you can ask all sorts of questions. So if you look at our paper, we have a list of questions, different questions that are kind of in this vein, let's say, about the various representations. So what can we get for polars and so on? If you have two sequences for primal and dual, can you get a convex set, right? Such that you get primal sequence for the primal, dual sequence for the dual. What can you represent it with? Maybe in some cases you can get spectrahedra, in some cases you can get spectrahedral shadows, things like this, right? And the final question is, you don't have to only look at dimensions in individual faces. You can also look at the dimensions of unions of faces. So we can think about something like this. So we can take the set of all faces of a given dimension. So maybe I can call it something like FD, right? So it's all union of all faces such that the dimension of the space is exactly B. So if we look at polytops, that's a very neat thing, right? Because if I take zero-dimensional faces, there's finitely many zero-dimensional faces. If I take the union of these zero-dimensional faces, the dimension is going to be zero, right? And so on. But you can get something very complicated. So you can take, say, the sphere or the Euclidean ball, and then project the fractal set on it, right? And take the convex hull of that projection of a fractal set. Like just draw a Sierpinski triangle on this, just on the surface, right? And then just only leave this Sierpinski triangle and take the convex hull. So in that case, you can have those things of non-integer dimensions, right? So you take the union of all extreme points of something weird like this, and the dimension of this is not going to be integer, right? It's possible to calculate this. It's not the dimension of the convex set. It's a Hausdorff dimension of a non-convex set, right? The union of all faces, right? So the questions we can ask is, what are the possibilities, right? So what are the possibilities for if somebody gives you this sequence I, and also another sequence that tells you the unions of my faces of given dimensions should have dimension 2 and 3, 7, and square root of 2, but not so. Can I find that kind of set? Right, so that's question 3. What is possible for I, and in addition to this original sequence, we get those dimensions of unions of faces. Right, so of course, if you restrict to semi-algebraic sets, something like this, then dimensions will be integer, but also we can go pretty wild with this and consider general convex set. Okay, I think that's enough, especially for Friday. So thank you very much. Yeah, they're facially exposed. Yeah, yeah. But the jewels are not. Yeah, the poles are not. Thank you.
So one thing I was wondering about was, so you have several equations there about the minimal number, but these are very special, right? So it's separable, right? Why not? Why is it not possible to have one equation? Because I mean, you can have a lot of faces. You just have one inequality, right? So you can still have at different points the face dimension of the face could be different, or am I getting something wrong here?
I'm not sure I understood. So it is a very special case. So in general, if I was doing something like this, right? So you give me a facial dimension signature, and I'm trying to produce a best represented closed convex set, and I write it like this, then that's a legitimate question, right? Why did you separate the variables? Of course, you could do better with, right, mixing things up and doing something more sophisticated. For this specific case, when you have the sequence that starts with 0 and ends with this, we have proved that you cannot do better. So maybe there's other constructions, but this gives the smallest possible number of inequalities. I'm not sure if that, yeah.
Are not exactly bound in terms, because they talk about the rank, which is essentially the dimension of faces.
I have not thought about that at all, so I don't know. It's a good question.
Thanks.
Yeah, thank you.
May I help?
Yeah, please.
Expanding. So on the first question, and if you take a single convex quadratic inequality, in the paper we characterize, you can only get 2. You cannot get more than that. Now, if you consider a highly nonlinear inequality, say polynomial inequality, I think that single inequality is not going to be fine. So, you know, imagine, think about the significant problems. But of course,
Right. Even quadratics, so the indices, I assume you're applying some theorem of the alternative. So you can't get a base. But that's why that was smaller spectrahedral rules are. And then the question about the bar, so that's about that's about so it only makes.
Thank you very much for expanding.
Here you use like log k dimension, I guess. Okay, like is this construction that you shown with like this thing, when you blow it up, it's going to be log k, I guess, log dimension of the whole stack. And you prove that you can achieve the sequence which is log n, when n is the dimension of the ambient space. Is there some example of signature where you cannot do better than square root n? Or do you have some construction?
No. No, it will be a very good thing to.
So log n
Right.
might be the right answer.
We don't know.
Okay.
So we right. Maybe Levent knows.
There,
But actually, I'm thinking you can probably get something from the lower bound, right? Yes. Yeah. 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 Sorry.
But when you say it could, you know the construction? No, okay.
I think that would be really cool to even numerically calculate some of the values, because you can actually do it, right? You can write different integer sequences and actually calculate the values. I think that will be very valuable. Yeah.